Greetings and welcome to another Reinblock screencast. In this screencast, I'm going to give you an introduction to Yul, which is a assembly language that is used in Solidity. In fact, it is an intermediary language that sits between the Solidity code and the compiled byte code. So let me give you a quick intro as to what Yul is and when you can use it and why you use it, as well as what the benefits are for using it. So basically, if you use Yul, you'll get a better understanding of how the Solidity language works, and it will help you to debug and solve problems in your Solidity programming code experience. So sometimes, when you're programming in Solidity, you can be guided by the compiler errors. And this is all well and good, but you need to know what is driving those errors and why that is happening and why you're seeing those errors. And assembly, by going into assembly, will help you understand that and help you get a deeper understanding as to how Solidity behaves the way it does. For example, you might have some questions like, why is it that you can't do a Kekak 256 of 50 directly, but you can do it if you pass in the ABI encode of 50? Or for example, why are you unable to append to arrays in memory, but you can append to arrays in storage? So these kind of questions can be answered once you get a familiarity with the Yul programming language. So what are some of the benefits of learning how to program in Yul? Well, there are a couple that come to mind. One of them is that when Solidity is upgraded, the new changes in the language are often only initially available in Yul. And so this might be of benefit to developers who want to take advantage of these new APIs as early as possible. And the other thing that is of benefit is contracts written in Yul or functions written in Yul can often have more efficient gas usage. And so you can use Yul either directly in your contract in an assembly block, or you can actually write Yul contracts 100% if you want to. And these contracts, as I mentioned, very often are much more gas efficient. Now, this doesn't come without some kind of Finally, what are the basics of Yul? Well, this slide here doesn't cover all the basics, but it does cover some of the things that you should be aware of, and the fact that Yul is a very basic language in the sense that it doesn't provide all the syntactic sugar and the helpers that you're used to when writing contracts in Solidity. So what Yul does not have is it does not have storage variables. It does not manage memory for you. It does not have arrays. It does not parse function arguments, and it does not provide that many data types. Well, actually, it only provides one data type. And so what we're going to do in the next section is we'll open up an editor and we'll start playing around with Yul, and we'll start off with looking at the one available data type that we can use in Yul programming. So I'm going to show you a basic example here of types in Solidity and then in Yul. So the first type we're going to look at is basically a number, a uint 256, which is the type that you've probably used quite a lot in Solidity. And so what I'll do is I'll create a function here in pure Solidity first of all that will return a uint 256. So the way you do this in Solidity is you write the function and then you give the function a name. So let's just call it number type. And then we make this an external pure function which returns the uint 256. Uint 256 like that. And then in the function itself we can define a uint 256 and we can call it x equals, and give it a value of 99, and then we can return x. Now I've got this to automatically compile. So that's already compiled, no errors. Let's deploy the contract and let's expand out the contract that we've deployed. So let's, and we can call the function. We can see it's got 99, which is this. Now, how do we convert this to use an assembly block in Yul so that we can return value x? Well, let's get rid of everything except the definition of x in Solidity. And then we can write an assembly block like so. And we can actually assign the variable x inside the assembly block using this syntax. So let's assign it a variable number of 88, and then let's return that. So now what's interesting here is you can see that we are assigning using this syntax. The other thing you notice is that the Yul, or the assembly block here, doesn't require semicolons, and that this x is actually able to reach out of the scope and read this value of x. So there's sort of like a shared scope here. So let's remove this contract and deploy the new version, expand it out and call the function. And as you can see, we get 88. So this is working. This is our first version of a Solidity contract using an assembly block written in Yul. So let's take a look at a different type. Let's have this set in assembly. Let's set the value using hexadecimal. So if I copy this function, and what I'll do is I'll just rename this to X type. Okay. And what I'm going to do in this function is I'm still going to return a uint256, but in the assembly block, I'm going to assign x to a hexadecimal representation of a number. So let's set it to, let's say, 0xc. So 0xc is the number 12 in decimal. So let's return that. Let's compile it and return it. So let me get rid of this one, deploy, and call the hex type. And we see we get the number 12. So what's happened here is that in assembly, we have used hexadecimal when setting the variable x, but in Solidity, it has interpreted it as a uint256 and returned the decimal version, which is of course 12. So now let's move on to a more interesting data type, strings. So let's create a function definition called string type, which is an external pure function that returns a string in memory. And then what we'll do is we'll create a definition of the string memory here, and we'll call this str, and we'll set it to an empty string to start with. And then we'll have an assembly block as we've had in the previous examples, and we'll have str, and we'll set that equal to a string, let's say hello, and we will return that string. So far so good. Now, we're getting a compiler error here. This is because I've got the space. Okay, now I can remove that contract and deploy it, and let's see what happens when we call the string type, which is here. We actually don't get any output, and we actually saw something in the logs here, which is an out of gas error. So what's the problem? Well, actually the reason is because we're using memory. So we've defined this string as being in memory, but in assembly we're dealing with pointers. So the string variable here is essentially on the memory heap, but the string variable here, when we're setting it, is setting a pointer on the stack. So these two things are not really compatible. So what we need to do is we need to use bytes 32 instead, because bytes 32 types are on the stack. So if we change this to bytes 32, then we can use this, and we can set the string. And let's see what happens now. Oh, we need to change the return type. Yes, that's right. We need to just return the type here. That's now bytes 32 because we changed it. All right, that compiles, and let's see what we get. So if we deploy that and run and call the string type, we actually get a value back. So we don't get a revert, we don't get out of gas, but we don't get our string back either because it's a bytes 32. And the way that we can fix this is to convert the bytes 32 back into a string when we before we return it here. So the way to do that is you use the string type, and we use ABI encode, and we ABI encode the string variable and pass that into the string type here. So we're casting it to a string, and then we just have to change the return type again to a string memory. And then it will compile without error, and we can deploy and test this function again. And this time, when we call the string type, we get the word back that we expect, hello. So what's happening here is we're dealing with bytes 32 so that we can set the pointer to the correct value as expected, and then converting it back or casting it back to a string so that we can return it as a string. Now, one thing to bear in mind is that we can only handle 32 bytes. So if I create a string that's larger than 32 bytes, maybe something like this, we immediately get an error here saying that the string literal is too long. So basically anything longer than 32 bytes is not supported in assembly like this because we're dealing with bytes 32. So the way around this will be discussed later on, but for now, this is how we can deal with small strings, which is via converting back to a string using ABI encode. Right, let's deal with another type this time. Let's use a Boolean, for example. And in this case, we can see quite clearly how Solidity will convert the bytes 32 that is set in the assembly code back to something that is a specific type in Solidity. So let's create the function definition again. So function, and we call this bool type, and this is an external pure function that returns a bool. And we're going to use Solidity. So what we're going to do is start off by, as we've done before, declaring the variable in Solidity first. So this will be a Boolean. And then in the assembly block, we'll set the Boolean. In assembly, we need to set the Boolean to, well, we can set it to anything we like, but let's just set it to 1 for now and see what happens if we return it. So we can come back over here and we can deploy the contract, expand it out, and click on bool type. Now the interesting thing here that you'll notice, it returns true, even though we only set 1 in the assembly code. This is because in Solidity, a Boolean is represented as a 32-byte word with the last bit set to 1. And well, more specifically, the Boolean is true when the last bit is 1, and it's false when the last bit is 0. So here essentially what we're doing when I change this to 0 is changing our last bit to a 0. So if I deploy this and check the Boolean type again, this time it's false. Well, let's try one more type. Let's try something interesting again. Let's use this same function, just copy it. And this time I'm going to try out address. So like so, address type, call it A. And let's set it as, actually ADDR, like that. Okay, is our variable name. Let's set it to 1. And let's make sure that we return that. So what are we going to get? Well, what happens here is, again, this is a 32-byte word in assembly, essentially. What we're doing is we're just setting the last bit to 1. And so what we end up with is that it will parse this, and Solidity will return us a valid Solidity address with the last bit as 1. So if we remove that and deploy again, and this time we can call the address function, we get an address back with the last number set to 1. I'd like to now move on to some examples where we can see certain operations being performed in a Yul assembly block. So in this example here, I've got a function that returns whether or not a parameter that's passed in, let's say this parameter here, n, is actually a prime number. And the work is being done in this assembly block. And the cool thing about this example is we get to see quite a few things with Yul. A good example here of using arithmetic functions such as add and div. There's also mod for modulus. There's a for loop example and an if statement, as well as setting variables and checking less than and is 0. So what's really going on here? Well, as we know, we got this contract which is written in Solidity, and we pass in the variable n, and we set this variable here called is prime to true. Now note, it's defined up here in the returns statement, so we don't have to declare that it's a boolean, it's already declared up here. Now we set the default to true, and what we do is we basically say, well, if the number that's passed in can at any point be divided by any other number, then it will return or set the variable to be false. And here, of course, as you know, we have to set that to 0, since inside assembly we're dealing with bytes 32. So what we do here is we're basically just halving the value that we pass in, and then we have this for loop which goes from 2 up to the limit here, which is less than half of the value, and we keep iterating and incrementing I. And for each iteration we check, is the modulus of this 0, meaning can we divide by this number I, and if we can, then that means it's not a prime, so we set this is prime to false. As I said here, it's a 0, and then we break. Now there are a few things that we can note about this. One thing is that these statements here can be placed outside of the block. So for example, this let I equals 2 can also be placed outside here before, so that's still valid. And we can also place this part here if we want to be outside or within the actual loop itself. And as you can see, it still compiles. But we still need to keep these statements here, these braces that need to be there as sort of placeholders. So this is one example of using different functions and different operations in Yul. So let's deploy this and just check that it actually works. So if we deploy the contract and expand it out, we've got this function here is prime. So if we say is 2 a prime number, then it returns true. If 15 is 15 a prime number, no, it returns false. How about 101? Is 101 a prime number? Yes, it's true. So this function is a good example for getting started with certain operations in Yul. Now, by the way, if you want to see more or have a full documentation on the Yul functions, you can head over to the Solidity docs, and there is a section in the Solidity docs for Yul instruction set. And as you can see here, if we scroll down, we can see some of the functions that we've been using, as well as some other functions like sub and not, and we've got less than and greater than and equal, and so on and so on. And this is the is 0 helper. So hopefully this is a good way for you to get started with writing operations in Yul. In Yul, to check if something is true or false is different from how it would be done in Solidity. This is because, as mentioned, Yul only has one data type, which is a 32-byte word. And so the only way we can really check for truthiness and falsiness is to check the last bit in a 32-bit word. And the bit would be set to 0 if it is falsy, and it would be set to another any other number for it being truthy. So here we have an example of a truthy statement. In this case, we have a value which is a result of uint 256, which we set to 88. Then in this assembly block, I've said if 99, which of course is basically just always going to resolve to true in this block here in assembly, then the result will be set to 99. So if we run this, if we deploy and call the function, then we will see that check truthy returns 99. Now conversely, if we want to check for falsiness, I can copy this function here and paste it down here. And in this case, what we can do is we can check for falsiness. So a falsy. And in this case, what we'll do is we'll say, well, we'll keep the result to be 88. But here we're going to say if 0, then the result is 99. But it will remain as 88 because this resolves to false. So therefore, this block here will not get executed and it will remain with the value set to 88. So let's give that a try. We'll deploy this contract. So I'll just remove that one first, deploy it, expand it out. And now if we hit falsy, we can see the return value is 88 as expected. In this example function, I'm making use of the is0 helper in assembly. And what we're doing here is we're just checking that is0 will return true when the value passed into that function is actually 0. And this is a way that we can perform negation of values in assembly using Yul. So here in this example, we got the result set to 1. But because this statement here inside the assembly block will resolve to true because 0 is 0, this actually will return a bytes 32 word with the last bit set to 1. This means that this is treated as a true result, which will then set this to 2, and therefore this will return true. So if we take a look at that, we can deploy the contract and we can run the function to check negation, and we get 2 as expected. Now in this example, I want to just cover quickly how you would not use not for negation. Now why is this? Well, in this example, you can see that not 0 actually would be fine. This would be resulting in a truthy statement, and then we would get this set. So the result starts at 1, this comes in here, not 0 results in true because not 0 typically would be 1, right? So we know that is going to be the case, and so therefore it would come back as true and set the result to true. So if we have a look at that, we can take a look at the negation. We can see here the result is as expected, it's true. Now what does this not statement actually do in assembly? Well, I've written another function here that just returns the output of not 0. And really what this will do is it flips all the bits and sets everything to the highest possible value, which is F in hexadecimal. And this is basically the not of 0. So 0 is 0x and then 0, 0, 0, 0. But the not of that is 0x FFFF, right? So if we take a look at that, I've already deployed this, not 0, you can see returns this. So therefore, given that fact, if we now copy this function and we paste it down here, and let's say we want to do negation with 2, so we're going to say not 2, well, this will still be truthy, and it's not behaving as we would expect. So because this is truthy, the result will still be set to 2, which is unexpected. So if we look at this, and we look at the negation 2, we can see the result is still returning as true. So in other words, what we should be using here is the is0 helper instead. So let me just return that and deploy and run the function again, and now we get 1 as the result because is02 is false, so this never gets run. So the moral of this story is don't use not when you want to check for negation and checking for 0, always use this is0 helper. The last thing I'd like to cover in this video is the fact that there is no else statement available in Yul. So in this example function here, I've declared to get the maximum between two variables x and y. And as you can see in the assembly block, we are just checking if x is greater than y, so we use the GT helper function, and if x is greater than y, we set max to x, and if y is greater than x, we set max to y. By the way, this max variable is defined over here in the return statement of the actual Solidity function definition. So if we want, we can call the function over here. I've already done it. 101 and 88 returns 101. If we have 56 and 44, then we get 56. So this function works, but the point is that there is no else statement in Yul. Now, one of the things that you might find useful is, again, in the documentation relating to comparisons and other functions. So let me just hop over to that again and just show you. So we've got things like and or and XOR. All of these things work in the same way as you'd expect from Solidity and perhaps other C-like languages. So like and is a bitwise and of x and y, and or is a bitwise or of x and y, and so on and so on. So I encourage you to take a look at this documentation in order to familiarize yourself with the various functions that are available in Yul. Now, I will end the screencast here so that you can take some time to experiment with Yul in your own time and use Remix as I have. And I will continue this series in another screencast where we'll start to dive deeper into the functionality of Yul. So until then, enjoy your programming experience, and I'll see you next time.